Hello, I am Peng Boyan from the University of Melbourne, and I will introduce SecRSL security separation logic for C11 release acquire concurrency. This is joint work with Toby Murray. SecRSL is the first separation logic for proving information flow security of C11's release acquire concurrency, and it formalized information flow security for axiomatic memory model for the first time. It allows us to prove information flow security for more efficient programs than prior logics. First, I will introduce information flow and C11's concurrency model. Then I will talk about our security definition, our logic, and its soundness proof. Finally, I will show you how we apply the logic so far. Many programs deal with sensitive data, and sometimes we do not want that sensitive information leaked. For example, consider the classic input boxes on most login pages. The account box or the email box in this picture will reveal what we typed, but password box may hide what we typed for security reasons. Intuitively, if we assume what we typed is some sensitive data, we say that the email box will definitely leak that information, whereas the password box will hide it. Our goal is to design a program logic to prove when programs will not leak sensitive information. This kind of logic must talk about pairs of program executions. To say why, suppose we type two different emails and passwords on this website, as shown by these two pictures. Then we can say that the email box leaks what we typed because its output differs between the two pictures. By contrast, assuming the length of the two different passwords is fixed, then the output of the password box is identical. Formally, we say a program does not leak its input if for any two inputs x and x prime, the program's outputs are identical and thus indistinguishable to observers. We call this information flow security. The concept of indistinguishability is key, and we will return to it later. There are existing programs logics to prove that programs are information flow secure, but none of them are suitable for C11's weak memory concurrency, which is the motivation of our work. Modern programming languages adopt the so-called weak memory concurrency models, which allow concurrent programs to execute efficiently on modern hardware. However, this model also allows for unintuitive behaviors. To tame these unexpected behaviors, C11 introduces various access modes to be used when accessing shared data from multiple threads. Consider, for example, the left program, which has two threads and uses a location A to synchronize these two threads. The initial value in A is 0, and the left thread will write 1 to A after it updates B. At the same time, the right thread reads A repeatedly until A is not 0, which means the value of A was changed by the left thread. We might assume that if the right thread reads B after that, the value of B will be 200, but under weak memory concurrency, this is not guaranteed to be true. To enforce this guarantee, we must decorate the shared variable accesses with access modes as shown on the right. We use the release mode when the left thread writes to A and the acquire mode when the right thread reads A. The non-atomic mode used for location B is the default. So what does this have to do with information flow? Well, consider that instead of transmitting the value 200, the left thread instead wishes to transmit some possibly sensitive data to the right thread, along with a flag indicating whether the transmitted data is sensitive. For the program to be secure, the right thread must reliably receive not only the data, but also the flag that denotes its sensitivity. Otherwise, it might inadvertently leak that data. This style of communication is common in concurrent applications that handle sensitive data. C11's weak memory semantic is formalized as an axiomatic model. This model does not directly describe memory states and transition between them. Instead, possible programs executions are represented as graphs. where each node represents a read, write, or allocation action on a location. And the graph's edges represent various relations between those actions. Moreover, because of the inherent non-determinism of weak memory concurrency, there may be many possible executions of one program. The two graphs in the slide shows two possible executions of the previous example program. In this program, the right thread has a while loop that may execute once, twice, or even an unbounded number of times, where the last iteration must read one from A and synchronize with the left thread, denoted by the red arrow in the picture. Because of this loop, the number of this program's possible executions is infinite. The main challenge of this research is how to apply the idea of information flow security to C11's axiomatic weak memory model and how to prove the soundness and the compositionality of the new security logic we developed. Prior security separation logic like SecRSL are defined over operational rather than axiomatic models and do not handle weak memory concurrency. The prior logic RSL does reason about C11 programs under its axiomatic model, but only over individual program executions, which means it cannot talk about information flow security. Luckily, these two works provided us an ideal starting point. The first question we solved is what does information flow security mean in an axiomatic model? In other words, what does it mean for two program executions to be indistinguishable when they are represented as set of graphs? Our solution is that we see two sets of graphs are indistinguishable if there exists a one-to-one mapping between these two sets that pairs indistinguishable graphs together, as shown on the slide. Formally, this means for any graph in one set, there exists an indistinguishable graph in the other set. Then the next question is what does it mean for two graphs to be indistinguishable? We say that two graphs are indistinguishable if they are isomorphic and every pair of corresponding nodes that accesses an attacker observable memory location must be identical. This captures the idea that two executions are indistinguishable when they both perform the same actions at the same times to attacker observable locations. Our logic SecRSL guarantees that any program satisfying its rule must be information flow secure. The judgments of SecRSL contain 6 parts. The pre and post in the braces are the traditional precondition and postcondition of our logic. The E and E prime in the middle are two symmetric programs that we want to prove are secure, where the only difference between them is that the sensitive data in them may be different. The HP and HQ in the brackets denote the set of high memory locations before and after the programs execute. These locations are allowed to store sensitive data. Our logic includes the standard rule of Howe logic and separation logic, as well as rules specific to C11. For example, the non-atomic write rules depicted on the slide describe when two writes to a location L are indistinguishable. The first premise requires that if the location L is not in the high location set, then we can only write indistinguishable value into it. The second premise requires that the location must have been allocated already. We prove the soundness of our logic in Cork by extending a prior formalization of RSL. The main challenge of the soundness proof was to prove the compositionality of our new security definition that relates execution graphs inductively over the graph structure. We briefly describe the high-level structure of SecRSL's soundness proof in comparison to the non-security logic RSL that reasons only about single program executions. This picture shows an execution graph where node 1 is the initial program action, node 2 forks the programs to two threads, and node 3 and 4 synchronize the two threads. Node 6 is the final program action. RSL proves the safety of the graph inductively. First, that the subgraph containing only node 1 is safe. Then, given node 1 is safe, that the subgraph containing just the node 1 and 2 is safe. When it reaches the two threads, there may be multiple possibilities to extend the subgraph. RSL requires all possible extensions to be proved safe. At the same time, to support the high conversationality of separation logic, for example, the frame rule, RSL's soundness statements quantifies over all possible contexts that might surround the graph. In the picture, node 8 and 9 are one such context. RSL establishes the safety of the graph inductively, assuming that the context is also safe. In SecRSL, we must not only reason about pairs of graphs under arbitrary execution context, but we must prove an additional obligation. For any graph of the left program E, there must exist an indistinguishable graph in the right program E prime. We do so by following the same inductive structure over the left graph, while constructing the right graph as the induction proceeds. This slide shows a possible middle state of the inductive proof. We have proved that the left subgraph of green nodes are safe, and we have also proved the existence of the indistinguishable blue right subgraph. The blue right subgraph grows as the induction proceeds over the green left subgraph until it covers the entirety of both executions, proving them indistinguishable. Finally, we prove the blue graph is an execution of E prime. Completing this final proof requires us to keep extra information in the inductive construction of the right executions, namely that it is what we call partially consistent. This inductive argument was the key technique challenge we had to overcome to prove SecRSL sound. See our paper for more information. Besides the theory, we also implemented, verified, and evaluated several versions of a secure synchronized channel abstraction common in message passing applications. We compared the performance of the versions which are proved secure by our new logic to a sequentially consistent baseline that cannot observe big memory effects. As shown, SecRSL allows us to prove the security of implementations that are significantly faster than their traditional counterparts. Finally, we conclude that proving information flow security for programs under C11's weak memory model is possible, and SecRSL is the first security separation logic for doing so. SecRSL also formalized information flow security for axiomatic memory model for the first time. SecRSL allows significant performance improvement compared to sequentially consistent baselines. Also, we believe our idea should carry over also to more sophisticated logics like ISL's successor FSL and FSL++, which would allow it to reason about C11 programs with memory fences. Additionally, we leave such investigations for future work. Thank you.